found it funny when he started dancing. Welcome to another exciting edition of HL Chemistry Flipped Classroom. My name is Mr. Los, and welcome. Okay, so today we're going to be talking about electron configurations, kind of electrons in general, some detailed stuff about how they are found in atoms and how they're arranged. So, electrons can be said to exist at certain primary energy levels. So if this is the nucleus and these are different energy levels, electrons exist in these certain primary energy levels. And there are 7 of them in the ground state anyway, and it's no accident that there's also 7 rows in the periodic table. The 7 primary energy levels correspond to those 7 rows in ways that we'll be talking about more. You will see energy levels often represented by N. In other words, like N equals 2 equals the second energy level. So basically what we're going to be talking about is ways to talk about where electrons are at, or ways to locate electrons. For instance, take your specific place where you're sitting right now. You know, you're on planet Earth. You're in the United States of America. You are in the state of Colorado, presumably. City of Aurora, perhaps. And so we can get more and more specific down to, City of Aurora to your specific house address. We can be more and more specific about where your location is. Well, it's similar with electrons. We can be more and more specific in talking about where they're at. We can talk about the primary energy level. That's the biggest division. And within primary energy levels, these are broken down into what we call sublevels or subshells, and these are named by letters, S, P, D, and F. And then each sublevel may have 1 or more orbitals in them. So again, we're getting more and more specific. Orbitals hold no more than 2 electrons. They hold 2 electrons maximum. So when we're looking at these orbitals, it's important that you have this information. And let me explain how to interpret this chart. So what I'm talking about here is N, the different primary energy levels. There are 7 of them, at least in what we call the ground state, 1 through 7. So in the first primary energy level, there's only 1 type of suborbital, which is S. And what you see in brackets is how many orbitals are in that sublevel. So there is only, in the primary energy level of 1, the first primary energy level, there is a S sublevel, and S sublevels have 1 orbital. Orbitals hold 2 electrons, so 2 electrons maximum can fit in the first level. In the second primary energy level, there is S sublevels, which have 1 orbital. That's what the bracket means. There are P sublevels, which there are 3 p orbitals. Now, orbitals hold 2 electrons maximum, so 1 plus 3 is 4. 4 orbitals times 2. 8 total electrons can fit in the second primary energy level. When we get to the third energy level, there are 3 sublevels available. There is the S sublevel, which again has 1 orbital. There is the P sublevel, which has 3 orbitals. And there is the D, which has 5 orbitals. 5 plus 3 plus 1, that's 9. 9 times 2 is 18. So there's 18 possible electrons that can fit in the third energy level, and so on and so forth here. Once we get down to the fourth primary energy level, we get to the what we call the F sublevel, which has 7 orbitals. And if you add all that up, there's 16 possible orbitals. Once you get to energy levels 4 and above, that's 32 electrons. Now I know what you're thinking, especially if you've never had any experiences before. You can, this is a little bit like a cat looking at a ceiling fan for the first time. It's a little confusing. It's a little stunning. Some of your faces might look a little bit like these cats right now. But we're going to keep talking about this, and it will become clear as we do more examples and other things like that. So let's keep it going here. There's a guy named Werner Heisenberg, and he developed what's called the uncertainty principle. And what the uncertainty principle tells us is it's impossible to know precisely. It is impossible to precisely know both position and momentum of an electron simultaneously. Basically, you can think about it like this. We can know where the electron is. We can know how the electron's moving. The more we know about one of those things, the less we know about the other. It's a little bit like trying to locate a bus by shooting a rocket launcher at it. If you happen to hit the bus with the rocket, you've found the bus, but you've also changed the bus in the process. Electrons are similar to this. The very act of detecting them can actually change where they are. So we can't know about both of these things at the same time. So we don't say where electrons are exactly. We talk about these orbitals, which are defined as a region in which an electron spends 95% of its time. So these orbitals, we're going to look at their shapes in a second, is the region in which 95% of the time that particular electron will be there. The other 5% of the time, it might be elsewhere. It might be doing other weird things. Electrons are weird, but the orbital is a region where it's going to spend 95% of its time there, or there's a 95% chance to find it there, if you want to look at it that way. Orbitals within the same sublevel and energy level are considered equal in energy. In other words, there are, in the 2p energy level, there are 3p orbitals. We call them the 2p orbitals. So those 2p orbitals are equivalent in energy, but they would be greater in energy than the 2s orbitals. So within the same sublevel and same energy level, orbitals are considered equal in energy. They call them degenerate. You'll see that word there, degenerate orbitals, which means they're equal in energy. One thing you need to know about is the orbital shapes. Now, you've all seen little graphs that give rise to shapes like y equals x squared. Of course, you probably know that's kind of a parabola type shape like that. Oops, I drew it a little bit wrong, but I think you get the idea. Well, in real life, so there's an x-axis, a y-axis. That's normally the kind that's flat on our page. But in real life, there's also a z-axis. There's this third dimension of space. And if you're a real smart guy like this guy Schrodinger, who wrote these equations, not only can you write equations like this that give rise to simple shapes, but you can write fancy equations that give rise to three-dimensional shapes. And that's what he did. He wrote a series of equations that tell us the shapes of these orbitals. So you do need to specifically know the shapes of the s and the p orbitals. The s orbital is very easy. It's just a sphere, so a sphere that sits right in the middle of the axis like that. That's what the s orbitals look like, and whether it's 1s, 2s, 3s, it doesn't matter. They're basically different sized spheres, and that's really all we need to know about that. For the p orbitals, there are 3 of them. Okay, they are often described as dumbbell shaped. So one of these dumbbells sits on the x-axis, that is one orbital. Another orbital sits on the y-axis, so they call this one px, they call this one py, and the one that's straight up and down is pz. So remember, what this means is orbitals hold 2 electrons maximum, so basically this is a region where I have a 95% chance of sort of finding those electrons at any given time. They're going to be sort of hanging out in here generally, and there's going to be another 2 sort of hanging out in this area, and then there's another 2 hanging out in this up and down dumbbell shaped area. There are other orbitals. There are the d orbitals. You don't need to specifically know the shape of them, but I'm just showing them to you for completeness here. They call these double dumbbells sometimes, and there's this weird like pacifier looking one. And remember, there's 5 d orbitals, so 1, 2, 3, 4, 5. There are 7 f orbitals, which again have some very odd shapes like this. Don't need to know the shapes for d and f, but that is what they look like. So now is the time when you're going to want to get out your periodic table, and we're going to decorate it. We're going to make some adjustments. We're going to draw some things on it. And so grab that out now. One thing that you can do, which would be wise, is to label your periodic table thusly with these different blocks. This is called the S block, the D block, the P block, and the F block. If you know where these blocks are, the periodic table can help you remember how many orbitals are in each, I should say how many orbitals are in each type of sublevel. Okay, so basically each box on the periodic table represents another electron. Lithium has 3 electrons, beryllium has 4, 5, 6, and so on. So each box represents an electron. So for instance, if you recall, there are 3 p orbitals. Orbitals hold 2 electrons. So notice there's 1, 2, 3, 4, 5, 6 boxes here in the p block. Remember, there are 5 d orbitals. Orbitals hold 2 electrons, so we'd expect there to be 10 here, and there is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 electrons, 5 d orbitals, 5 times 2 is 10. Here, the s block, since there's only one s orbital, there's only 2 here. Orbitals hold 2 electrons. And then F remember, 7f orbitals. So if you look down at the F block, there should be 14 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. These yellow ones are kind of, don't worry about what's going on with those. It's not important for right now. But basically, if you just remember where these blocks are and you divide however many squares are in that block divided by 2, that would tell you how many orbitals are in that particular type of sublevel. So we're going to talk about some rules, and by the way, we're going to add some more to your periodic table later, so keep that handy. What these are is, if you can imagine, let's say that I am making from scratch, I'm making a gold atom. So I start with a gold nucleus, and then I start dropping electrons into that nucleus. There are some rules about how these electrons will slot in and fill into the orbitals. The Aufbau principle is the first rule, which says electrons are going to go to the lowest energy orbitals first, and once those are full, they're going to move on from there. Hund's rule says only one electron will occupy an orbital at a time until they are forced to double up. And then we have the Pauli exclusion principle, which is orbitals hold 2 electrons max, and then these orbitals have opposite spins. So all these things seem a little complicated. When we do examples, they're not quite as complicated as they seem, at least at the level that we're going to have to use them. Hund's rule, one way to kind of remember that is I call that the bus rule. So imagine, you're on a public bus, okay, nobody knows each other, and there's all these little these are bus seats. That's what they're supposed to be right here. So you walk in, maybe it's early in the morning, there's nobody at all on the bus, and you walk in, and these are 2 seats. Each of these holds 2 people, let's say. So you get down and you sit right there. And then we have a new person who walks in. Now imagine, again, it's a completely empty bus. Here's a stranger. This new person comes down and plops down right next to you there. You're probably going to think they're a complete weirdo, and probably no one would ever do that. They would go sit somewhere else. This dude's going to sit right here instead. And then another person comes into the bus and sits here. Another person comes to the bus and sits here. And let's say they, maybe there's only 4 seats on this bus. It's a short bus. So once these 4 seats are full, finally when the next person comes in, they're going to have to sit there. They're going to have to double up. So just like people on a bus, electrons don't double up in orbitals unless they are forced to. And we are going to be drawing what we call orbital diagrams. Orbital diagrams show the location of electrons in a particular atom or ion. And again, these are not very hard to do. Once you see me do some examples here, I think this stuff will kind of come together a little better for you. And lines or boxes represent orbitals, and arrows represent electrons. Electrons have a property called spin, and the direction the arrow points is going to represent that spin. It's called counterclockwise and clockwise spin often. So it's not necessarily literally what's happening, but you can sort of imagine the little electron spinning in one direction and then spinning in the opposite direction. So if we're going to draw some orbital diagrams for lithium, nitrogen, and silicon, jot these down real quickly, and then I want to I'll show you what we're going to do with them. You're going to want your periodic table to help you draw these orbital diagrams. Okay, so looking back at our periodic table here, and we're going to draw what's called an orbital diagram for lithium. So I know where we're going to start off, and you will see how I know this better as we do more examples, and look, there's a way to sort of decorate your periodic table that is helpful here. And as a matter of fact, let's just look at that right now. Sorry about that. Yeah, before we go any further, let's do this to our periodic table. There's some things I want you to write in it. And I want you to write 1s, like right in this box that says 1s. And that says 2s, and that says 3s, 4s, 5s, 6s, 7s. So right in that box. In this box, I want you to write 3d, and 4d, and 5d, and 6d. And then in this box right here, I want you to write 2p, 3p, 4p, 5p, 6p. You can put 7p down there. 4f, 5f down here. Now, even if your table looks a little bit different than this one, you should be able to have the general idea here of of these labeling. So make sure you do that before we try this next part. Okay, so lithium. I'm going to start with 1s, and I'm going to draw a single line. And then I'm going to go to 2s and draw another line. Now I know to do that because of the way that, well, because I have these orbitals memorized for one thing, but also because of the way that I've drawn this periodic table. Basically, reading this table, like you'd read anything, top to bottom, left to right, tells you the order to list the orbitals in. The first one I come to is 1s, and I make a single line because that represents a single orbital. The next thing I come to is 2s. I'm going to make a single line to represent that 2s orbital, and then I'm going to stop because lithium's right here and I don't need to go any further. So in the first orbital, there's going to be 2 electrons. And by the way, we're starting with the lowest energy down here at the bottom, and we're going up to higher energy. So remember, electrons fill the lowest energy orbitals first. So 2 electrons would go in that first energy level, and then a second, or a third rather, electron would go in this orbital and energy level, and then I would stop because that's 3 electrons, and lithium, that's what lithium has. It has 3 electrons. That's its atomic number. And that's it for lithium. That's an orbital diagram for lithium. So let's say I was doing nitrogen. I think that was your next one. I hope so. That's what we'll do anyway. So I'm scoping out where nitrogen is. I notice it has 7 electrons, so I'm going to put 7 arrows in my diagram. I'm starting with 1s, and I'm writing a single line because s orbitals, there's only 1 s orbital. And then the next thing I see is I see 2s, and I'm going to draw a line here. And then I come to 2p next, and there are 3 p orbitals. There's 6 boxes in the p block, divided by 2 is 3. There are 3 p orbitals. So I need to put 7 electrons in these boxes following the rules. They fill the lowest energy orbitals first, which are these ones down at the bottom. So 2 electrons go there. 2 electrons go there. So that's 1, 2, 3, 4. Now I have 3 electrons left, and I'm going to put them in these boxes. Now, what you don't want to do is you don't want to do that, because the problem with that is you're not following Hund's rule. You're not following the bus rule. These electrons are not going to double up until they have to. So that's not going to be right. What we're going to do instead is this. 2 electrons in this orbital, 2 electrons in this orbital. There's 3 more electrons to go. Basically, these electrons, the reason for this is these electrons, they just want to spread themselves out as much as possible. Electrons are negative and they repel each other. So rather than doubling up in one of these slots, they're each going to go into a separate orbital. And that is the orbital diagram for nitrogen. Okay, so now we have silicon. So silicon is element 14. It's right there on the periodic table. It has 14 electrons. I'm going to start out with 1s and make a line because there's a single s orbital. I can tell because there's 2 boxes here. 2s comes next. Make 1 line. 2p, 1, 2, 3, 3 lines. 6 boxes here divided by 2. There are 3 p orbitals. What comes next after that, again, I'm just reading left to right, top to bottom. So on my diagram, what comes next is 3s, and then what comes after 3s is 3p. There are 3p orbitals, so I'm going to make 3 lines. And then I'm going to start filling in electrons till I get to 14. We fill in the lowest energy level first, which is that one. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now 2 more electrons to go. I need to spread them out as much as I can. I'm going to put 1 in this and 1 in this. A couple of things here real quick. Notice that even though one of these p orbitals is empty, there's nothing in it. Notice I still drew it in my orbital diagram. It actually is important to know when there's empty orbitals. And the second thing is you do want to draw, in this type of situation, you want to draw both your arrows in the same direction, either both up or both down. Electrons like this, when there's 1 electron per orbital, they would have the same spins. So that's the quick rundown on orbital diagrams. It's one of these things that seems kind of confusing at first, but I promise You'll get the hang of it. It's not that difficult, and we will be doing more examples. Back the video up and look at it again too if you're having some trouble. Okay, so just the last thing I want to have here in these notes is talk about electron configurations. Electron configurations, what they do is they're going to list. They're similar to orbital diagrams in that they're talking about where the electrons are, but you're going to do it in a much more compact fashion. And in an electron configuration, electrons in the lowest energy level are listed first, and they get higher in energy as you go. So when you're doing an electron configuration, you're starting with the lowest energy, and you're going up to the highest energy. And this is not necessarily the same in terms of how far they are from the nucleus, which is going to become important. But the way we list the electrons is not necessarily their distance from the nucleus. Usually it is, but not necessarily. It's an order of energy. So, for instance, going back to silicon here, we have silicon's orbital diagram. If I was going to write the electron configuration for this, what I would do is, so I see 1s and there's 2 electrons in it. So I would go 1s2, and then 2s, and there's 2 electrons in the 2s orbitals, so I'd put a 2 there. And then I'd go 2p. There are 6 electrons in the 2p orbitals, so I would put a 6 there. In 3s, there's 2 electrons in the 3s orbitals, and then in 3p, there are 2 electrons. So all of this is an orbital diagram, kind of becomes this, an electron configuration, which is quite a bit easier and faster to write. So that's all for now, guys. We're definitely going to be practicing a lot more with writing electron configurations and all that stuff. I promise you, doing this, once you get the hang of it, is actually super easy. We'll learn how to write these like directly without writing an orbital diagram first. But thanks very much for listening and watching, and we will see you next time.